Yeah, so in this video we are going to expand upon the topics that we touched in the previous video. So in the previous video we talked about the bootstrap method, in particular the leave one out bootstrap or out of back bootstrap, how I call it, for constructing confidence intervals empirically. And in this video we are going to talk about two advanced bootstrapping techniques. One is called the 0.632 bootstrap and one is called the 0.632 plus bootstrap. They're both related, and where the numbers come from we will then see in this video. But yeah, just to briefly recap the bootstrap procedure. So what we did is we had a data set and then we were constructing these bootstrap samples. So for each bootstrap sample we sampled with replacement. So we then would fit a model on each of these samples, and then so we fit it on here, and then we evaluate the model on these out-of-back samples. So in the previous video I also showed you how to implement that in Python, how you can do the out-of-back bootstrapping procedure in Python. Here I also have some code that I implemented to do this a little bit more conveniently instead of re-implementing it every time you want to use it. So one is the object-oriented implementation that I made. I implemented this in Eval extend. It's just called Bootstrap OutofBack. And how it works is that you give it the number of splits, so the number of bootstrap rounds, and you set a random seed. And then, let me clear this here, what you then can do is you can iterate over the train and test splits. So there's a split function. So first you initialize this object. I will actually explain why I did that so complicated. It's to mimic the k-fold cross-validation or k-fold class in scikit-learn, and because that allows us to use this method as a cross-validator object in grid search and other things. But more about that later when we use actually grid search. So first we initialize this out-of-back bootstrap object with the number of bootstrap rounds and a random seed, like I said. And there is this split method, and this split method just gets the data array here. So you could do that on the test set, for example, or the training set, or just the data set. It doesn't really matter. What it is doing, it is separating whatever you give here into two subsets. Here it's, let's say, the train and test subset. And on the left-hand side, so this is just iterating and then printing that out. On the left-hand side, these are our bootstrap samples. And on the right-hand side, these are our out-of-back samples. So if I go back one slide, these green ones here are the ones here, and the ones shown here in red, those are these here. So this is just implementing what we had on the previous slide. So why doing it so complicated? Like I said, it allows us to plug that into, let's say, grid search later, because it mimics the k-fold or certified k-fold cross-validation classes in scikit-learn. So we haven't talked about k-fold cross-validation yet. We will talk about that in the next lecture. But let's focus on the bootstrap for now. So here, this is just the data loading, the usual data loading. So we load the iris dataset, then we split the iris dataset into a training and a test subset, and we initialize a decision tree classifier here. And we also implement or load a method called cross-val_score. This is a scikit-learn function for doing k-fold cross-validation. It has an argument that is called CV, and we can set it to, let's say, 5 to do 5-fold cross-validation, which we'll be talking about next week. But we can also, instead of giving it an integer, we can also give it a k-fold or any cross-validation object. The only requirement for this one is that it's an integer, or it has to be something that has like this split method. So in our case, our bootstrap out-of-back object has the split method that divides the dataset into a training and a test subset. So we can actually provide that here. So see here, I'm plugging in my bootstrap out-of-back thing into this cross-validation score function. And yeah, then what it does, it's performing this out-of-back bootstrapping here. So here, this is the average score. This is just a standard deviation, and then we can also use our percentile method to get the confidence interval. Because the Bootstrap scores, it's a list of all the accuracies. This would be a list of the 200 accuracies from the out-of-back evaluation. So that was the object-oriented API. Just to go back a little bit, the reason why I was implementing it in this object-oriented way is that we can then plug it into this cross-val score, and this is quite convenient. And later we will see there's a grid search class which has also this CV argument. So in that way it's convenient to have it implemented like that, because if we wanted to, we can use this out-of-back Bootstrap for cross-validation and model selection in grid search. But there's also an easier implementation, or implementation that is easier to use, that I implemented in MLExtend. And this is called, I called it Bootstrap 0.632 score. Why the 0.632 here? Because we will later see we can use the same function for the 632 and the 632 plus Bootstrap. By default, it's doing the 632 Bootstrap, which is why I call the function like that. But you can choose what type of Bootstrap you want to use by specifying this method here. So here OOB is the out-of-back case, and this should give us the same result as before. I think, why are the numbers different? I think it's, has maybe something to do with the random seed here. I don't know why I did use a different random seed. Anyways, so it's another function that can compute the out-of-back Bootstrap a little bit more conveniently. So all you have to do is you have to provide it with the classifier, the training set, the number of splits, and then a random seed. And then again, so you can compute the mean accuracy, and then also the percentiles for doing the confidence interval. So the confidence interval would be here. So that is another easier way to use the Bootstrap method. Okay, now let's talk about one shortcoming of this out-of-back Bootstrap. So as Bradley Efron described in 1983, that there is a pessimistic bias of the out-of-back Bootstrap, and the 0.632 estimate improves upon the pessimistic bias. So why is there a pessimistic bias? It comes back to the fact that we have now a smaller data set. Recall when we talked about the holdout method, we have a data set, and then we split it into a training set and a test set. But the model could benefit from more data, right? So now we have a smaller data set. In the case of the Bootstrap, out-of-back Bootstrap, it's the same thing. If I go back here, we have these training subsets and the out-of-back samples. So there are out-of-back samples that are not included here in the Bootstrap round. So in that way, the estimate for the model may be lower compared to a model, how it would perform if it was fit to the whole training set. So one more time, let me go back. So if we fit a model on this Bootstrap sample here and evaluate it on the out-of-back sample, this model fit on this Bootstrap round is likely weaker than the real model that we would fit on the original data set, because the original data set contains more training example. I mean, the sample size is in both cases n, but here we have duplicated data points, right? So in this case, here are more, in the original data set, there are more different examples. So this is actually a stronger model. We would expect it's a better model if you think of the learning curves context. So to address this pessimistic bias, Efron suggested this 0.632 estimate. And here also, I just want to mention that the pessimistic bias in the classic Bootstrap method, so the out-of-back Bootstrap method, can be attributed to the fact that the Bootstrap samples only contain about 63% of the unique samples from the original dataset. So in fact, when we divide the dataset, when we do the Bootstrap sampling into a Bootstrap sample and the out-of-back sample, only 63.2% of the data points in the Bootstrap samples are unique. Why are only 63% of the training examples unique in each Bootstrap round? So we discussed that back then in the ensemble method lecture, but let's just recap that. So we have the original dataset, let's call that original. And then we have our Bootstrap sample here. So what happens is if we do the Bootstrap sampling, we randomly pick data point for each 1 to n position here. We randomly pick a data point and then put it into our Bootstrap sample until we reach the sample size n. So it could be like this. And it could also happen that we pick the same example multiple times, right? Because it's sampling with replacement. So the probability of choosing a particular point for a position. So let's say the probability for this point to pick exactly this example. So the probability of picking this example here is 1 over n, right? Because we have a training set or original data set of size n. So the probability of picking one particular example for a particular position is 1 over n. So not picking this example for this position would be 1 over n, so 1 minus 1 over n, right? So that would be the probability of not picking this example here. But we have n picks, we pick n times, so we have 1, 2, 3, 4, 5, 6, up to n picks. So we have the probability of not choosing a data point is this value here, 1 minus 1 over n to the power of n, because we repeat this n times, right? So this is the probability of not choosing a data point. And it just happens then if n is really large, for some reason, I mean, we don't have to go into detail about that, it can be approximated by 1 over e, but what's more important is that if n goes to infinity, that this value is 0.368, so we have a 63.8% probability of not including a data point in the Bootstrap sample. So vice versa, if we have a 36.8% probability of not choosing a data point for the Bootstrap sample, that means consequently only 63.2% of the data points in the Bootstrap sample are unique. So this is the probability of not choosing an example, and 1 minus this is the probability of choosing an example for the Bootstrap set. So only 63% of the data points are unique, and that is where the pessimistic bias comes from. So the training set only has 63% of the unique examples in each Bootstrap round compared to the original data set. So here's just a visualization of how that behaves for different sizes of n. So this is if we have at least 200. Usually in practice we use Bootstrap samples, at least 200 Bootstrap rounds. So here's just a plot how that behaves for different sample sizes, so different sizes of n for the sample size, not the Bootstrap rounds, it's the sample size here. So you can see for sample sizes about 100 to 200 we already have like value between 64 and let's say around 3.5% only of the examples are unique in the Bootstrap sample. Okay, so now how is that related to the 0.632 Bootstrap method? So the 632 Bootstrap method tries to address the pessimistic bias of the OutofBack Bootstrap, and that is by using both the OutofBack samples and the Bootstrap samples to compute the accuracy in each round. So in each round, now the accuracy is computed as follows. So we have two terms. There's term 1 and term 2, and they get added together. That's for each Bootstrap round. And this one here, this is the familiar accuracy on the OutofBack sample. So here this is the accuracy for the OutofBack sample, OutofBack accuracy, and I should maybe use the same color. Let's do this in green. So this is OutofBack accuracy, and then the second term here, this one is the resubstitution accuracy. So here, this is the resubstitution. So if we have the original data set and we split it into, let's say, a Bootstrap sample, and then we have the out-of-back here. This is the out-of-back, and this is the blue, the Bootstrap sample. If we have a model, we fit it to the Bootstrap and we evaluate it on the out-of-back, right? So this is the out-of-back performance, and this on the right hand side is the resubstitution accuracy. This one, you know, is optimistic, overly optimistic, because it's the same data that the model has seen, because that's what the data that was used to fit the model. And we just learned on the previous slide that the out-of-back one is pessimistic. And the goal is then to combine a pessimistic and an optimistic estimate together to get a more, I would say, realistic estimate that is not overly pessimistic and also not overly optimistic. So how do we do that in practice? So here is an implementation, again, in MLExtend. So that's the same function we used before, the Bootstrap 0.632 score method. So before we set method to OOB. We set the method parameter inside here. However, here we don't have to do that because the default parameter for this function is the 0.632 bootstrap. So by default, it will do the 0.632 bootstrap. So we do also again 200 rounds, provide the training data set a random seed, and then this will the bootstrap scores will be the accuracies in each round. So the bootstrap scores will be these accuracies. Let me use a different color, it's getting crowded. So these accuracies, and then we sum over these accuracies and then compute the average. So that's the average accuracy, the mean of the list of these here, which is what we compute here by just averaging over them. We can then use our percentile method to get the confidence interval. So we have the mean bootstrap performance here the confidence interval, and yeah, that's how we use the 0.632 bootstrap. Now, the story is not over. So the 0.632 bootstrap attempts to address the pessimistic bias of the out-of-back estimate, which is an optimistic, which results in an optimistic bias because now we have also the resubstitution accuracy. So we have both the out-of-back accuracy and the resubstitution accuracy, and this could now lead to a more optimistic bias. So if I go back, we combined this pessimistic estimate with this optimistic estimate, but this may outweigh the pessimistic one, so the whole method may be slightly over optimistic. So what do? Yeah, there's also a method for that. It's called the 0.632 plus bootstrap. So notice the plus here. What's the difference between the 0.632 and the 0.632 plus method? So here in the 0.632 plus method, we have a flexible weight that depends on the data set. So in the regular 0.632 method, we had a fixed weight. You can think of it as a fixed weight where we set this value here for the out-of-back accuracy. We set it to 0.632, and then this value here will be 1 minus 0.632, which is 0.368. So we had these fixed weights. We used for this one the 0.632 and for this one the 0.368 in the previous slide. So just going back, so yeah, you can see that here. So we had these two values here. Now we just use omega like a flexible weight, and this is computed as follows. So how do we compute this? So this one is computed by taking the 0.632 and dividing it by 1 minus the other value, 0.368 times R. So what is R? R is the relative overfitting rate. So here is an overfitting correction factor in play. And how is that one calculated? So it's kind of like following a rabbit hole here. So first we have omega, and then in omega we need R, and R is computed as follows. But in R we have another unknown, it's this gamma here. So how does that one get computed? So here's another fresh slide where I have a little more space. So we have talked about R, the relative overfitting rate, which includes this gamma here. And gamma is the no information rate. So the no information rate is the performance of a model if there is no information in the data set. So you can think of combining each training example with each possible class label. So if you have the iris data set, think of taking every flower in the iris data set and duplicating it. So we have now 150 times 3 flowers. So we have 450 flowers. And for each flower we have each class label. So we have 150 setosa and the same 150 flowers labeled as virginica and the same 150 flowers labeled as versicolor. So there's absolutely no information in this dataset because every data point can have any possible class label. And that's how we compute this gamma here. So we go over these all the possible combinations here. So here this is for a binary classification problem, which is why I have the 1 over n here, the 1 over n squared. For our case here above, this would be of course n cubed. Okay, so this looks all very complicated. You don't have to implement that by hand because I've already done that for you. So again, I implemented this in MLextend. So here it's again our familiar Bootstrap 0.632 score method. And if you choose the option 0.632 plus, it will perform this 0.632 plus Bootstrap. So again, the same approach. We get the mean Bootstrap score and the confidence interval. Okay, so this is it. These are all the different Bootstrap methods. Now let us take a look at how they compare to each other. So I have done some simulation here on the iris dataset and the MNIST dataset, a 5,000 subset for 5,000 MNIST images. But let's talk about the iris dataset first. So what we have here is at the bottom the normal approximation confidence interval, which is based on the test set, so there's no bootstrap involved here. Then I have the bootstrapping of the test set, and here I have our OutofBack, the regular bootstrap, but using the sample confidence interval method, like the if we have the sample mean, let's say x bar plus minus t, you can also use z if you want to, times the standard error. And here, same thing with the percentile method, and you can see they are like expected, almost identical. So the difference is percentile method is more like based on the distribution of the sample means, and here we compute that by dividing over the square root of n. So if we would estimate it, but in our case, we compute just the standard deviation of the distribution of the sample means, which we have because we repeat the bootstrapping. We discussed that before, so don't need to go into too much detail here now. But then the interesting parts are the 0.632 bootstrap method here and the 0.632 plus bootstrap method. And like we said, so the regular bootstrap, the OutofBack bootstrap, can be pessimistically biased. So it's a little bit lower compared to, for example, the 0.632 bootstrap. So the 0.632 bootstrap corrects this pessimistic bias. So it's also even now a little bit over optimistic, as we talked about. And the 0.632 plus bootstrap, this is the one that corrects the slight optimistic bias of the 0.632 bootstrap. So you can see it's slightly below. So this is pessimistic. This is optimistic, too optimistic, slightly too optimistic, and this is like the corrected version of that. So in practice, which one to use? If you don't do any model tuning and you just want to know how well the model performs, you just take the data set, and I would say do the 0.632 plus Bootstrap to do a confidence interval of your model estimate. If you so one thing with that is you have multiple models, so you don't know exactly the performance of a single model, which is fine though, because you can just do that. You can construct the confidence intervals. So if you have a data set, you want to know how well the model performs, you just do the bootstrapping on that data set. You get the confidence interval and the mean performance, and then you just fit the classifier on this original data set, and then you can expect that the performance of this classifier fit on the original data set is about the performance of this 0.632 plus Bootstrap plus the confidence interval. In deep learning, this can be very expensive. So in deep learning, this is something that might be hard to do because we have large sample sizes. So in that case, I would say maybe doing the normal approximation interval might be fine. You can also bootstrap the test set, but there's also, you can see a little difference between the two. So you can just do the normal approximation confidence interval if you have a very large data set and neural networks that are maybe not very stable and have convergent, not always converge when you train them. So for large sample sizes, I think the normal approximation interval is fine. Usually I would recommend though the 0.632 plus Bootstrap. So here at the bottom, I was doing the same thing for a different data set. So the MNIST data set, where I have a 5,000 sample subset and a decision tree classifier. And you can see again, these two methods agree with each other as expected. They agree with each other as expected. This is like, again, the pessimistic one. And this one is a little bit too optimistic. And this one is the corrected one, the 0.632 plus method. But you can see now whether we use this method or this method, there's quite a difference. So which is the correct one? It's hard to tell. I mean, this is computed based on the test set. This is computed based on the data set. Which one is more trustworthy? It's hard to tell. It also looks like they are very far apart, but it's actually not that far. So this would be about, let's say, 77 point, I don't know, let's say 5%. It's hidden, I can't really see. And this one would be 82.5. So it's actually quite a bit. It's 5% apart. So which one is the more trustworthy one? It's hard to tell, right? One is on the test set and one is based on this bootstrapping here. But yeah, I really recommend, I think, using the 0.632 plus method if you can, because it has been developed for that. Here, this is given that it's a decision tree which is noisy on MNIST, this can be just bad luck due to variance, because when we compute or when you split the data set into a training and a test set, there might be some variance, so it might be coincidental here. So this one is a little bit more reliable, because if you think about it, we repeat something for 200 rounds, so we fit a model 200 times. Here, this one is just based on a single model. So in that way, I would trust the 0.632 plus Bootstrap a little bit more than the normal approximation confidence interval. Okay, so yeah, this was it now for the resampling methods. We talked about the holdout method. We talked about constructing simple confidence intervals with a normal approximation interval. We talked about the repeated holdout method, the empirical confidence intervals. So actually in practice, like I said, I would do the empirical confidence intervals if you can. If it's too expensive, the normal approximation intervals are fine. In practice, usually I wouldn't necessarily do the repeated holdout. I would rather do the bootstrapping. And in the next lecture, we will also take a look at some other techniques, cross-validation, which are very useful for hyperparameter tuning, model selection, and even algorithm selection. Okay, so then, yeah, see you next week.